Okay, welcome back to class. And let's see. I'm getting unexpected results here. Okay, back. All right. Tonight, we have a few things to do. Number one, I want to discuss the second exam, so I'm going to go over this. You don't see that, do you? Anyway, I'm going to go over the second exam in detail, and hopefully that will give you the information you need to answer any questions that are out there regarding grading. If not, please let me know. And by the way, you should always do things like this. Add up the points, make sure I got them right. When I score these papers, what I do is I put points on each problem, and then I put the total at the bottom. So it's actually a good idea to check to make sure you got all your points on each page too. So if I made an error, I'll be happy to correct it. Sometimes, of course, there's a disagreement, in which case I'll try to be reasonable, but I'll listen to what you have to say. But I don't guarantee we'll agree at the end. After the exam, I'm talking about the exam. I also want to talk about, go over a couple of things about power series. Once again, we introduced them last time, but I know that was right before the exam, so I'm not so unrealistic to expect that everyone, in addition to cramming for the exam, instantly did all the problems and went out and read a couple of other textbooks and maybe got their old calculus book out and read the chapter on that and said, oh yeah, now I remember. Wouldn't that be nice? But most of us live in a world that doesn't have that much time. So I'm going to do a little reminder on that. Then I'm going to do a couple of examples of solving differential equations by means of power series. And there is a 10th homework already posted to Blackboard, which is due on Thursday. It's very short. I think it's like 5 problems, maybe 6. But they'll be similar to the things that I'm going to talk about tonight. And the only reason I'm doing that is I actually thought of just making it due on a week from today. But I thought, you know, if you're in a situation where you didn't catch up with the series stuff last week, and then if next time I jump into the deep into the pool on series, then that would not be a good situation for anybody who was, you know, not current on the material. So it's a short assignment, but I did make it due for Thursday. Okay, so as usual, if you're attending online, feel free to speak up at some time that seems as appropriate as you can find anyway, if you need to get my attention. And I think that everyone should be seeing, should be looking at the key for this exam as I am. If that's not the case, let me know and I'll see if I can figure it out. Okay, the first exam was to solve this differential equation here. And this one has the nice feature of being separable. you can put this term, x squared plus x plus 2 times y squared, put that over on the right-hand side of the equation where it would pick up a negative sign. Then you can divide through by the y squared, integrating both sides. Y to the minus 2 has antiderivative minus 1 y to the minus 1. And that uses up that minus sign there. That's why it's gone from here. And then taking the antiderivative of this polynomial, you get x cubed over 3, x squared over 2, 2x plus c1. And then you take the reciprocal of both sides. Now, it's actually okay if you have the form where you just have this 1 over that. I accepted that for full credit. But it's kind of nice to multiply the numerator and denominator by 6 to clear out the fractions and get this form here. So any question about that one? Oh, and every problem is worth 6 points. Where there's reason to do so, I'll say a little bit about how I distributed the points. But for most of these, they're relatively short, so there's not a lot to say. Okay, the next one is a first order linear equation. It's got a y prime and a y. At present, there's a 1 on the right-hand side, but the leading coefficient is not 1, and it should be 1 to get it in standard form. Now, that doesn't mean that you have to put it in that form if you've got some other way of attacking the problem. But if you're going to use the formula for first order linear, then you'd want to get it in the standard form, which is this right here. Y prime plus 3 over xy equals x to the minus 4. And we have a formula for that. You know, there is something, oh, I see, this slid. Let's see if I can adjust here a bit. I'm having to reach a long way to get to the paper. Okay. I have to align, realign. All right, I think that's going to work. All right, so dividing through by x to the 4 to get the standard form, and then here's the formula for the first order linear equation. H is an antiderivative of the coefficient on y, and that gives you log of x cubed. So y is then e to the minus log of x cubed, or you could take the minus up into the exponent, add a minus out here, and put it as log of x to the minus 3. Then you have e to the log of x to the minus 3 is x to the minus 3. That's how this comes. The other one, reciprocal of that, because I don't have a negative in the exponent here, x to the 4, and we're left with 1 over x, which integrates to log x then. The plus c, of course, is not in the integral, so it just stays plus c. And when you distribute the 1 over x cubed, you get this form here. And, you know, of course, there's various ways of writing that, but this form will do. Any question on that one? Okay, problem number 3. Now, in this case, I think there's a couple, at some points, there's more than one way to do it. So I'll comment on that when we get there. Consider this ODE, sine y dx plus cos y dy equals 0. Determine whether the equation is exact. And the standard way of doing that is you take the partial of the coefficient of dx, take its partial with respect to y, take the partial with the other coefficient with respect to x, and see if they are equal to each other. They are not. One is cosine y, the other one is 0, so this is not an exact equation. Show that e to the x is an integrating factor. Well, the way I did that, and the way I expected everybody to do it until I graded the papers, was, well, multiply this integrating factor means if you multiplied through by e to the x, this original, then you'd have an exact equation. So I multiplied by all the way through by e to the x, and then did this check, and it worked that time. The two partial derivatives are equal, and so that means that e to the x is an integrating factor. But when I was grading the papers, I realized there is another perfectly legitimate way to do this, and that is that we have a formula for an integrating factor. And if you apply that, and it pops out the value e to the x, well, you have definitely shown that e to the x is an integrating factor. So that's another way to approach it. And I suppose somebody somewhere will eventually think of yet a third way to do the problem. But those are the two ways that I would do it. And I think using the formula is fine. There's not really a problem with that. Okay, then we want to solve by using the methods of exact equations. Well, if you're going to use the method for exact equation, then it had better be exact when you do that, right? So you would definitely at this point want to take this original and multiply through by e to the x. If you do, then you have the equation e to the x sine y dx plus e to the x cos y dy equals 0. Pick one of those two and integrate it. I took the first one, e to the x sine y, integrated with respect to x. You could just as well find the integral of e to the x cos y dy, integrating with respect to y. Either one would do nicely. So if you integrate that, you get this general form here. But of course, at this point, we've already checked, so we have some insight into what g of y is going to turn out to be. And if you take the partial then of u with respect to y, you should be generating the second term in the original ODE after you've multiplied through by the integrating factor, of course. And this works by setting g prime equal to 0, which means that g is a constant, which means we don't really care about it, because whatever u is, we're going to set it equal to a constant. I don't care if you call it k or anything else. So e to the x sine of y equals a constant is the solution to the equation. I should note that a favorite error to make, and now I'm generalizing over the set of all students to whom I have taught this material, and I'm sure that I was prone to it myself when I was learning, is to stop at the point of computing u. Is to get to here, conclude that g is a constant, and say, oh, well, u is just e to the x sine y plus a constant. And when someone does that, it's always like cringe when I'm grading, because I think, you are a quarter of an inch from the finish line and didn't quite get there. The solution to the ODE is to find u, but then to set it equal to a constant. So if a function is equal to a constant, its total differential is 0, which is where this form comes from. Okay, any question on number 3? All right, number 4. We want to solve this differential equation. It's the operator x squared cap d squared plus 5x cap d plus 6y equals 0. I was pleased to see, I think absolutely everyone translated this correctly to x squared y double prime plus 5xy prime plus 6y equals 0. This is no Euler-Cauchy equation. In other words, we're going to be looking for solutions of the form x to the m or related things. So you might jump direct to this form, m squared plus 4m plus 6 equals 0. I put this in my key because I thought some people would probably do it this way. If you think of x to the m as the solution, then when you take the derivative, two derivatives, you have m minus 1, one derivative, 5x was already here, so you have 5, and then m for first derivative on x to the m plus 6. And if you solve that quadratic, you get 2 plus or minus root 2i. So the solution is x to the minus 2 times the quantity c1 cos root 2 log x plus c2 sine root 2 log x. really easy to get this confused with the form for constant coefficient equations, which when you have y double prime plus ay prime plus by equals 0, if you get a complex conjugate pair for the solution of the characteristic equation, then you have e to the alpha t times the quantity c1 cos beta t plus c2 sine beta t, assuming alpha plus I beta were the form of the two roots. So this is Euler-Cauchy, and it gets this form. Any question about that? Okay, next one. This one, I think, I can't remember for sure this time around, but typically on an exam, if I give one of these equations, a few people at first think, man, that looks like you ought to be able to separate, and you flail around for it with a while, and you find out that you can't. You can't just do algebra and get the y's on one side and the x's on the other. So then you have to think of something else. And at some point, you probably would realize that that this is just like a linear, first order linear, except it has power y multiplied on the right-hand side. We have a name for that. It's called a Bernoulli equation. And what you do is you set u equal to 1 minus a, where a is this exponent on y over here. If you use that substitution, then it will turn this into a linear equation. So this is a little bit more involved. You got to transform it to a linear, solve the linear, and then back out of the substitution. So we're going to set u equal to y to the minus 1. Now, you could take derivatives here. Some people do it that way, and it actually works out okay. You'd say u prime equals minus 1, u to the y to the minus 2. And then, you know, they work with it algebraically for a while, and they get the same thing I do, which after you simplify, when you do the substitution, you should get this first order linear equation. This one, you could solve by inspection, or you can solve by applying the formula. It doesn't matter. Either way, just so long as you solve it. When I saw this, I thought, oh my word, the solution to the homogeneous equation is, to me, immediately obvious because I've done this for so long. E to the x is its own derivative. So e to the x minus e to the x equals 0. C e to the x is going to be a part of the solution. And then I just want a linear ax plus b that comes out to be 2x here. And, you know, I fiddle around with it either on scrap paper or just thinking about it. And minus 2x minus 2 will do. Once you have that done, then you want to remember that u is equal to 1 over y. Y is 1 over u, so u is 1 over y. So this is not y, this is 1 over y. You take the reciprocal and maybe clean it up a little bit, and that will give you the solution. Now, if you don't like doing it by guess and check, which is essentially what I was doing, you could apply the first order linear formula for u, and you will find out that minus 2x minus 2 plus c e to the x is in fact u, and then you set that equal to 1 over y, take reciprocals, and you're done. Any question on that? Okay, problem number 6. Solve the initial value problem. So this one is a constant coefficient second order linear equation. So the first thing we do is write down the characteristic equation, lambda squared minus 6 lambda plus 9. Turns out we have a double real root here. So C1 e to the 3t, and C2 e to the 3t. By the way, you notice that the independent variable never shows up here. So you can call it t, x, or anything else you want. It doesn't matter. I chose t. So C1 plus C2t e to the 3t is the general solution. And then we plug in 0 for t to get this equation. When I plug in 0 for t, then this term goes to 0. This factor becomes 1. So it just tells me C1 equals -1. And then y prime, I compute the derivative and I plug in 0 for t, and I set y prime at 0 equal to 6. And I find out that C2 is 9. So -1 plus 9t times quantity e to the 3t is the particular solution for this initial value problem. Any question on that? Okay, problem 7. Find a particular solution. By the way, I noticed that a number of people actually found a general solution. They found both the solution to the homogeneous equation and the particular. That's fine if you did, but all you were required to do here was find the particular solution, which is this right here, 2x minus 3. And if you look closely, you'll see the remnants of a little whiteout, which means I made a mistake. Actually, I think I made a mistake copying this right here. And of course, it cascaded through the whole problem. And so then I had to decide, okay, do I want to tear this up and write a new key or get out the whiteout? So what did I do? I got out the whiteout. But this is one of the reasons why I like to provide some blank paper or blank backsides, at least on exams, because I know that happens to you too. Okay, so what we do is scan across here and say it is a constant coefficient, and I have a first order linear polynomial on the right hand side. So something of the form ax plus b should produce that right hand side. So you set y equal to ax plus b, take a couple of derivatives, and the derivatives are particularly nice here, which means I shouldn't have made an error down here, but I did anyway. So here I've got my derivatives. I plug them into the left-hand side and set them equal to 18x minus, and look at that. I got 39 here and 3 here. Looks, oh, I know what happened. I remember now. And besides, I can see a hint of it through there. I originally had 36. I flipped the 6 around in a couple of different ways, and the 9 around, and it turned into a 6. But that was wrong. It was supposed to be a 39. And that, of course, cascaded through the whole darn thing. So, which was too bad, because if you think about it, once you copied it wrong, then I got a solution, I did a check, it worked, and then I start grading papers, and everybody's getting it wrong. I mean, everybody's getting it wrong. And I thought, how can this be? So I went back and looked, oh, copied the problem wrong. Okay, well, it happens to everybody, right? Sooner or later. So anyway, if you copy it correctly and do all the algebra correctly, you find out that yp equals 2x minus 3, and it doesn't matter how many times you had to try to get that. As long as you got that, then that was full credit for solving problem number 7. And of course, this one, I think, isn't that the same as this one here? Yeah, minus 6 plus 9. Yes. So if you really did want to tell me the general solution, then you could just copy this. C1 plus C2, well, X then, because I got X on the next page. C1 plus C2X e to the 3X, and add it to this would give you, add it to that would give you the general solution. Or you could just do it a second time. That's fine too. Okay. I'm ready to leave number 7 unless I hear a question. Okay, problem number 8. Use the method of complex exponentials to find a particular solution. What you want to do is to, first of all, I recommend rewriting this as a complex solution. I noticed a few people as I was grading papers, not necessarily this particular problem here, but a few people are in the habit of writing down just enough of the step so that they can then create the next step. And that, if you're smart, that actually works reasonably well through high school mathematics. And if you're really pretty good at it, you can even make it work going through calculus. Sooner or later, though, it gets to the point where if you're doing that, you'll get into trouble. So, and the reason is it just gets so complex that you can't remember from one step to the next what you probably meant by what you wrote. So it's a good idea, not absolutely required, but it's a good idea to actually write out every step here. So I am injecting this into the complex plane. Here it is. And I'm assuming that z has this form. Then when I take one derivative on this, I'm going to simply get this coefficient 2i joining the constant k here. So I'll get first derivative will be 2ik, but I'm multiplying it by 5 here. That's where the 10i comes from. The 6 is simply copied. 2 derivatives, I'll have 2 copies, 2 factors of 2i. That's minus 4. It's 2i squared minus 4. And then I simplify this. 6 minus 4 is 2. 10i copies here. So it's 2 plus 10ik equals 6. I divide through by that coefficient, and now I just have to simplify it. Now, probably most people on the exam, when they were doing this, they did not do this step. It turns out you don't have to if you do if you take care of it on the step following. But it simplifies the arithmetic a little bit if you cancel out any common factor between numerator and denominator first. And I noticed that this has a 2 in it, and so does the numerator, so I took them out. 3 over 1 plus 5i, and then multiply top and bottom by the complex conjugate of the denominator, and you get this. And at that point, you can read off z is 3 over 26 minus 15 over 26i. And of course, remember, that's the k part. So that's multiplying e to the 2it. But e to the 2it is cosine 2t plus I sine 2t. Then, since we want the cosine part, that comes from the real part of the solution. So the particular solution is the real part of z, which is, you can get a real number in 2 ways. A real times a real, or an imaginary times an imaginary. So the real times a real is 3 over 26 cosine 2t, and the imaginary times imaginary. Well, first of all, when I take this times this, I'm going to have an I squared, and I already had a minus sign. Minus I squared is plus 1, so this would be a plus. And then it's 15 over 26 times sine 2t. So there is the particular solution. And that's how I did it. I think almost everybody who did this correctly actually didn't simplify here. So they had kind of a big denominator, but well, it worked. So it's hard to argue with success, isn't it? Okay, solve this differential equation. And this I intended you would do by variation of parameters. It might be the best way, I'm not sure. Other people observed, just by looking at this, well, first of all, you want to know what the homogeneous solution is, and it's going to be C1 times e to the minus C1 times e to the minus t plus C2t e to the minus t. Actually, I wonder if we did that before. Anyway, there's the basis for the solution of the homogeneous equations, homogeneous solutions. So that matters because you want to know whether this thing in the right-hand side overlaps the homogeneous solution. It does not. So you just can move ahead. If you're going to do it in the alternate way, you could make the observation, well, if I have an exponential times a sine or a cosine on the right-hand side, the only way to possibly get that would be to start with a particular solution of this form, e to the minus x times a cosine x plus b sine x. And then you could take a couple of derivatives on this. It gets rather messy, but you could take a couple of derivatives on that, plug it into the left-hand side, and then just use algebra to get what I'm going to get here by variation of parameters. That method is perfectly correct. And if you look at the problem, it doesn't say how to do it, right? It says solve it. So it's perfectly acceptable, and some people did pull it off. So good for you. I don't remember who, but somebody did. And a number of people made valiant efforts. So the problem is that the algebra gets pretty thick doing it that way. But, you know, it's correct. So, and in a working situation, it's not as unreasonable as it might seem on an exam. You know, if you get a page of algebra on an exam, that is not nice, because one little bug and things start falling apart. But in a situation where you're doing some engineering and you need the solution, well, you got more time, right? So if it takes you an extra 15 minutes, it doesn't make that much difference. So here's what I recommend, though, for doing this. Find the two basis solutions. So e to the minus t and t e to the minus t. Take their derivatives, plug them into the formula for the Vronsky, and you find out that the Vronsky is actually fairly simple, e to the minus 2t. Then you plug in the y1, the y2, the r, and the w. R is the right-hand side, e to the minus x cosine x, into the formula for variation of parameters. And after you plug it in and simplify, it is not impossible to do. It is not that nice, but it's doable. So you get e to the minus t times the integral of t cosine t dt. That's going to require parts. And this one, well, all of the muck canceled out. You're just left with a cosine here, and that's pretty easy to integrate. So that is just going to be a sine. So that's easy to handle. This one, if you call t, you call that u, and cos t dt, you call that dv, then you apply parts uv minus integral v du. And once you find this antiderivative and distribute, you get this form. And by wonderful good luck, the minus t e to the minus t sine t and the plus t e to the minus t sine t add out, and you're just left with e to the minus t cosine t. So, and how on earth do people ever come up with right-hand sides that have all that stuff cancel out at the end? They start here. That's how. You start with this, you take a couple of derivatives, plug them into this, and what you get is what you get. That's the right-hand side. So that's how you make up problems where everything magically cancels at the end of the problem. But that skill is very useful if you're teaching, but it's absolutely of no value whatever if you're doing engineering or science, because you don't get to make up your problems, right? So anyway, that's how I did it. And then you can toss on the homogeneous solution, C1 times Y1 and C2 times Y2, and you get this form here for the general solution. Any question? Okay, problem number 10. By the way, as you walk through the exam, what you find out is the problems do get harder or longer, one of the two, but the point values stay the same. That's intentional because most of the points can be accumulated by doing relatively short and straightforward problems. That's telling, purpose for that is it tells me whether people have basic competencies, and then as you get towards the end of the exam, I'm finding out whether you can handle the stuff that's more involved. But the point values don't go up, because if they did, if you have, you know, general competency, but you're not really great at it, you fail the exam, right? So it's intentional, and that makes this distribution of points more complicated. So number 10, even though it takes a page to write it out, is still only worth 6 points. You get 1 point for answering part A correctly. You get 3 points for coming up with the eigenvalues and eigenvectors, and you get 2 points for then solving the differential equation by using that. And I did try to be pretty consistent in the way I graded it. So I think probably that's uniform for everyone, but if not, let me know. Okay, without calculation, we can tell this matrix has 3 linearly independent eigenvectors. How do we know that? It's symmetric. Its transpose is equal to itself. Oh, and that's weird. Looks like it says underneath the whiteout symmetric. So I don't know why I whited it out. Yeah, it does. Anyway, A is symmetric, or you could say, give me the definition of symmetric, A transpose equals A. This or that or both will get you 1 point. So now we want to get the eigenvalues and the associated eigenvectors. So what we do is we subtract 3 down the diagonal, and then we take the determinant of the original matrix. And the easy way to do this one is to do a cofactor expansion. You'll notice along this row or along this column, there's only 1 non-zero entry. Furthermore, this is in a plus position. It goes plus, minus, plus, minus, plus. So 2 minus lambda times the 2 by 2 determinant with 3 minus lambda 4 on the first row, 4, 3 minus lambda on the second row. So 2 minus lambda times, take that product, 3 minus lambda squared, that product minus 16, and you clean it up a little bit, and you get, it factors to lambda minus 2, lambda minus 7, lambda plus 1, set it equal to 0, 7, 2, and minus 1 are the eigenvalues. I saw a couple of things when I was grading that I should mention. Some people, when they worked on this, they wanted to do this, at least partially, they wanted to do it by row reductions, which of course you can evaluate determinants that way. But remember to get all your lambdas in there before you start the row reduction process. Generally speaking, that creates a mess. So I have not had a lot of luck with that. But the truth is, you know, you can exploit any techniques any correct techniques you know, and it is true that you can evaluate determinants by row reductions. So if you would like to use that method, you know, have at it. And sometimes it might work pretty well. The other thing was, once you get the eigenvectors, then you have to find the once you find the eigenvalues, you got to find a linearly independent eigenvectors that pair with those values. So for instance, with lambda is 7, that's one of my values here. Then I subtract 7 down the main diagonal. So 3 minus 7 is minus 4. I'll get minus 4 here and here, and I'll get minus 5 there. So I get this matrix, and I want to find a non-zero vector in its null space. So in this case, it's pretty easy to do that by inspection. The vector 1, 1, 0 will do. And So I got 7 in that vector. Now, you know, somebody might say, well, no, I'd rather use 2, 2, 0, or a half, 0, or whatever. If you did it by MATLAB, what it will give you is 1 over root 2, 1 over root 2, 0. Why? Because it's adjusting the length of the vector to be 1. So it normalizes the vector. So it doesn't matter. Any non-zero multiple of that would be fine. And that pairs with lambda equals 7. Now that's going to reappear in the solution here. A constant times the eigenvector times e to the eigenvalue t. So that comes from this here. Then in a similar way, you take this form and you plug in 2, and you'll get this. And 0, 0, 1 is the eigenvector here. It is really tempting to look at this, and after your experience with 2 by 2 cases, to look at this and say, oh, minus 4, 1 will do. And had this come from a 2 by 2 system, it would have done, because on the 2 by 2 systems, the second row is always a constant multiple of the first row. But it is not the case here. So minus 4, 1 does not work, and 0, 0, 1 does. If you can't get it just by inspection, remember, it's always perfectly legal to go back to your earlier techniques for solving homogeneous systems of equations. You could take this thing here, put it in your calculator, get the row-reduced echelon form, and then write down the solution that corresponds with that. It would be fine. So that's another option. But anyway, 0, 0, 1 is good there. So I have e to the 2t, 0, 0, 1, and a constant for the next term in my solution of my ODE. And then finally, minus 1. When I subtract minus 1, I'm adding 1. So I get a block of 4s there and a 3 here. Well, minus 1, 1, 0 is a good solution for that. So that's the eigenvector. There's the eigenvalue in the exponent and a constant, and that gives me the general solution of this. It can happen on these that you don't get, if you have, say, a 3 by 3, you might get only 2 eigenvectors. What do you do then? Well, you can still do this process. It's just it's not all of the solutions. And you know, we could talk about what those look like. But it turns out, I've been told repeatedly by people who work in the field, that those sort of things virtually never come up in engineering. So why are you putting this in your engineering course? So I thought, okay, I'll take it out. The course is overstuffed already. So we use that little nugget of time somewhere else. Okay, any question about this? All right, one last one, number 11. And this one is one to really kind of pay attention to. Oh, look at that. There's actually a bug in my key here. Okay, it's fixed. Describe what each term in this differential equation is. Well, m times y double prime, that's mass times acceleration. That is the net force on the mass. There are 2 things contributing to the net force. There's a force due to damping, which is minus c times y prime, damping constant times velocity. And there is a force due to the spring, which is minus k times y. The minuses come from the following considerations. First of all, we just declare that our constants are going to be positive. However, damping always acts in the opposite direction of velocity, and the spring always pulls or pushes in the opposite direction of displacement. So you have negatives here, and I didn't leave much room for it, but the net force, my double prime, is equal to the damping force, add to that the spring force, and then when you push it all on the left-hand side, you get that differential equation. So full solution would be to say my double prime is net force minus cy prime, that's the force due to damping, minus ky, that's the force due to the spring. And that 2 circled there means that that was good for 2 points. And I had a hard time deciding how to split up the other 4, as you can see from the scratch outs. But in the end, I gave 3 points to solving this particular one and sketching a graph. And you should get a graph something like this. And then 1 point for identifying it as under damping. One thing I did notice on a number of papers where people sketch this graph here is that if they drew this with attenuation, so this is inside of an envelope that's declining in size exponentially, the most natural thing in the world to do when you sketch that is to draw something like this. Here's our axes, and then you do something like so, and then you say, okay, now I know that's got to be getting smaller. And people start drawing like this. And here's the problem. Look at the distance between the intercepts. They're getting shorter, right? But if you look at the equation, these omega here is 1. So that's a constant period. Well, it's not exactly periodic, right? But it's a constant amount of time it takes to find a max and a min. And so you don't want to scrunch them up like that. I don't know if I took off points for anybody for doing that, but if I saw it, I did try to mark it and write a note on there. Be careful when you sketch this. Those gaps should be constant. And of course, I don't do them perfectly either. So, but I was at least aware of the possibility of scrunching them and tried to avoid it. So let me mark this properly. I marked this because ages ago, I hope I didn't tell you this story already. I was a shiny new assistant professor, and I was teaching calculus too. And I got to some place in the course where there was a certain kind of error that I often see on papers. So I said to the students, please be careful, don't do this. And I wrote it up on the board, and then I explained why it was wrong and things like that. And then class came to an end, everybody filed out, and a notebook was left on the desk, one of the desks. And I thought, oh, I better pick that up and find out who it belongs to and give it back. And the student had very carefully written down the error as if it were correct and had written nothing about this being the incorrect way to do the problem. So I thought, okay, when people are taking notes, they're probably going to put on their paper what I put on the board. So if I want to be clear that this is an error, I should mark that. That's why I did that. And who knows, I probably still forget half the time. Okay, the percentage score on the exam was computed as simply the percentage of points you got compared to the maximum score that anyone achieved. If theoretically, what is there, 11 problems, 6 points apiece, theoretically there are 66 points available on this exam, but no one got it. And no one got terribly close even. So I think it was like 57.5, I think was the score. But you can easily find out, take your score and, you know, do the math, and you'll know what the maximum was. So that's how I came up with the scores. And therefore, the percentage score, when I do it that way, naturally somebody got 100 and other scores kind of trailed down from there. I should probably mention just a couple of things before I leave the exam part of the class. And the number one is you could look at this exam And if you just wrote down the topics, you would probably figure out what I was doing when I wrote this. This is a separable equation. This is a first order linear. This is a, well, it's related to an exact equation. Then Bernoulli, then second order linear homogeneous with constant coefficients, then non-homogeneous second order linear with constant coefficients, then a second method for the same kind, then second order linear constant coefficients, but non-homogeneous, and the method of undetermined coefficients doesn't work nicely. It does work, but it isn't nice. And then a system of linear differential equations. Well, that is basically an outline of that second part of the course. So what I do when I write exams is I actually start with an outline and I try to pick something from every area. And you know, I don't have a lot of leeway, because if I did 2 problems even out of every topic that we've discussed, you wouldn't get it done. So that is a hint about, you know, what to expect when you get to the exam, but it's also a hint in a case like this. It doesn't work so nicely for every topic, but on this topic, it really does work well for deciding how to solve the problems. If you have a mental list stored, these are the things that these are the kind of equations that we studied. Then you just, you know, you land on one of these things and you think, okay, how am I going to attack this? Well, let me see. This is first order. What are my options in first order? Well, first order equations, there weren't that many. They were separable, first order linear, Bernoulli, and exact. Okay, so one of those things is going to have to work here. And then you start looking through and saying, well, what might work? And in this case, you could separate it. So it actually has a couple of options. However, in this particular example, I told you what method. But on these others, for instance, you know, on this could be a really hard problem if you don't have an organizing scheme stored away mentally. If you have that, then you know there's a limited number of things that I could ask about, and you'll think of Bernoulli fairly soon. But if you don't have that list stored away, then you might get here and just, you know, you try to separate it, it doesn't separate, and then, you know, you try a couple other things and nothing seems to work and you give up and go on to another problem. So if that happened to you, the way to avoid it with differential equations, the basic differential equations, is to memorize that list of the types of things we did. And it'll help you out. Okay, so that ends the discussion of the exam, unless there are questions. Okay, last thing I just want to mention in passing is I did scan your exam, and I printed out a summary of your grades. And at least for everybody who has a GRCC email, I mailed that out to them earlier today, so you should have that. Should have that already. Of course, if you're attending in person, that doesn't much matter, because then I handed it to you on paper. But especially for those who are attending remotely, if you didn't notice it already, you should already have your exam back and a grade summary in your email. You should also have in your email an announcement that says there is a homework assignment due on Thursday. And it's pretty short, and I think you can all probably do it. But it would help if I gave you some examples like that. So that's the next topic for tonight. Since for once maybe the only time in the course. We are pretty much on schedule. So why don't we take about a 5-minute break? This computer says that it's 6:52. So at 6:57 by Microsoft time, I will restart, and you're welcome to take a break in between.
I think he gave me too many points.
Oh,
When I added up, I got 50.
Well, that's particularly disappointing.
Just have to do better in the next one.
Okay, thanks for telling me.
Yeah.
I should have sworn in the microphone. Oh, okay. Oh, this means it's a reduction that comes from what I consider to be a very minor error. And if you get two of them on the same page, it's deduction of one. But if you only one, just forget it. Okay, it's about time to start on the second half of the class. And what we want to do here is to do a little more work with power series, and then I want to show you some really basic examples of how to solve an ODE by using power series. Now, for the examples that I will be doing tonight, when you see them for solving ODEs, on all of them, I think you would look at the equation and say, well, I know the answer to that already. Why am I using a power series? The answer to that is I'm trying to teach you how to use the power series to solve ODEs. And then if you dig deeper into the subject, you get definitely the things you cannot solve by inspection. But I'll explain more on that in the next class period. There is one last point I'd like to make about the exam before I jump into these examples, though, and that is two things happen on this exam. One of them makes me always sad, and the other one is absolutely delightful. The sad thing is I had a student who was doing very, very well in this course who just didn't show up and didn't hear. So, you know, generally when that happens, it's for a reason. People who are doing very well in a course don't just walk away. There's a reason for it. So the only reason I say that to the people who are still attending is, you know, if something comes up, maybe it's something you really can't fix and you just have to leave. That happens. You know, there are family emergencies, illnesses, job changes, just all sorts of stuff. But I do actually care about people as well as mathematics. So if something comes up for you, it's really, it's nice to hear about it. And especially if there's some possibility that I could do something to help. So, you know, don't feel that you couldn't contact me if there were really extenuating circumstances. The second thing is that there was an example of somebody who had kind of a mediocre score on the first exam that really nailed it on the second one, and it's just delightful to see that. And I mention it because, you know, effort really oftentimes does pay off. And that's not to say that every time things don't go well, it's just a problem with effort. There are other aspects of life, but I do want to congratulate the people who made some significant investments and you know, pulled themselves up a notch or two. That's great. It does also happen, you know, that people slip down a notch or two on an exam. And that's one of the reasons I give the grade summaries. You know, you can do the math yourself. You know that there's going to be 3 exams and a aggregate score for the homework, and they all count equally. So you can tell if you are still in the game, and I think most people are. So, you know, just because you have a bad time of it on one exam doesn't mean that you should just give up. You can, most people, what that happens to, it is possible to pull out of the tailspin. So I encourage you to give that a good try. And if you're not sure, you know, it is okay to ask me. So, and I'm happy to offer advice. If somebody really does get in the situation where it's just, you know, it's obviously not going to work. If you had a low enough score now so that if I plug in 100 for the final exam, you still are nowhere near the boundary for passing, then, you know, yeah, you probably should put your time into something that's going to give you a better return for the rest of the semester. So, but that frankly doesn't happen very often. And I'm not, I don't think that anybody who's been taking the course seriously at this point is in that situation now. Okay, what I want to do is talk a little bit about power series, and because the time is limited, I am intending to basically do some examples, and I had a list of them here somewhere. Where did I put them? I can probably, there they are. Okay. I probably could pull it off without the list, but it's nice to do problems that I have actually tried and tested and find out can be done in a reasonable amount of effort. Okay, here's a function, 2 over 1 plus 5x squared. And what I want to do is to come up with a series expansion for this, a power series expansion. And I also want to determine where this converges. Power series, by the way, always converge somewhere. It might be just at a single point, but it will converge for some value. And I think that's all I want to do with this one. So how would I produce a series for this function? Now, there are a couple of ways you might approach it, but what I recommend on something like this would be to start with a known and not too awful series. This is the geometric series, kind of a simplified version, but it's the one to know for this class. The sum, m goes from 0 to infinity, x to the m is equal to 1 over 1 minus x. And I learned this in high school, but not in this form. I learned it in the form a r to the n goes from 0 to infinity, is a over 1 minus r. But the a is simply the first term. So if you set m equal to 0 in this formula, you get 1. And the x and the r in the other form are just the thing you are taking powers of as you march down the line. Okay, now why would I use that? Because I can easily do minor changes one step at a time and land here. That's why. So what I'm going to do first is I'm actually going to take one more step than I need to, but it's just because I want you to see what I'm doing. What I'm going to do is replace x by minus x. So I'm going to get 1 over 1 plus x. And then that means here, I have, where I used to have x, I now have minus x. And it's a good idea to clean this up a little bit. On this problem, things are simple enough that, you could leap to the final answer probably, or halfway through or something. But it's really a good habit to get into for the purpose for which we are using series, to always have a sum. And you could have other factors out here, but then you want x to the m generally. So not m plus 1 or m minus 1 or something like that. Now you could have 2m or 5m or something like such thing. If you have a coefficient on that m, there's nothing you can do for that. But plus or minus something, you can adjust it so that this will be m here. And you'll see how as we walk through some of these examples. Now, I'm getting there. The next thing I would probably want to do is get a 5x down here. So I'm going to replace x by 5x. In my previous series. And so that I've got the minus 1 to the m is still here, but then I have 5x to the m, which of course is 5 to the m, x to the m. Not too bad. We're almost there now. Okay, now remember, this thing is a function of x. And so f of x, if I write it without a series, and in a nice form for taking derivatives, is 1 plus 5x to the minus 1 power. So if I take its derivative, get minus 1 plus 5x to the minus 2 power. So minus, whoops, almost forgot, chain rule. Good heavens. Have to go back to calculus 1. So I've got this function now, minus 5 over 1 plus 5x squared. And I'm going to get that from this series here by taking a derivative. And I'm going to write m equals, and then I'm not going to put a 0. I'm leaving it blank. I'll tell you why in a minute. And then I'm going to take a derivative on that term. Okay, now keep in mind, when you're looking in here, the only variable is this right here, x to the m. Everything else is constant. So the derivative of x to the m is m times x to the m minus 1. So the minus 1 to the m part and the 5m part, that just stays the same. I pick up a factor of m, and this goes to m minus 1. Almost there. What I haven't done is put down my starting index here. Well, when m is 0, this is a constant times x to the 0. X to the 0 is 1. When I take the derivative on 1, I get 0, right? So that first term goes away. And the only one that counts, the first one that doesn't go away, is when x is raised to the first power. So this goes from, m goes from 1 to infinity. I lost that 0 because I took a derivative on a constant, and there's a 0 there. Now, you might think, well, wouldn't it just, it seems like if you're doing math, it should work, just to apply the formulas. So you go from here to here, and you still index it at 0. The truth is, it does still work, but it's inefficient, and it leads to complications later on. The reason it works is if you plug in a 0 here for m equals 0, you'll get a 0 there, and it'll blot out that first term anyway, right? So it does still work. But when you start shifting around indices, which is the next thing we're going to do, you could get into trouble. So what I'm going to do now is I deliberately started this at 1 to clean up any 0 term here. And now I'm going to drop this back down to 0. So the idea is on the outside of this sum, I'm reducing all the m's by 1. And the way I make up for that is I increase all the m's by 1 on the interior of the sum. And I get that. And we're pretty close now. So just to repeat what I did there is all these m's on the outside, I drop them by 1, and then on the inside, I replace m by m plus 1. So m plus 1 here, here, and minus 1 goes up to m. And you can always check to see if you did it right. What happens if you set m equal to 1, the first term in this series? Well, it would be minus 1 times 5 times 1 times 1. So minus 5, I guess, is what I get. If I set m equal to 0 in this, I still get minus 1 to the 1. So a minus 1, 5, and x to the 0, I get the same term. It worked. If I made a mistake and like dropped these on the outside and also dropped them in the inside, the first terms of those two series would not agree. Okay, anybody want to ask a follow-up on this? Because I usually get some questions when I do this.
Where'd the 1m go?
Oh, did I lose one?
From
Oh, I did.
line from
I
the
did.
bottom.
Thank you. For those listening online, the question was this: what happened to that m? Answer: I lost it. Which I think is a slang term for like lost control of my emotions or something. No, that didn't happen. I simply lost this vector. So normally we would write that like over here, right? But, okay, well, we're almost where we want to be. The goal was to land with this function here, 2 over 1 plus 5x squared. We've got the 1 plus 5x squared part now, but we'd like to have a plus 2 instead of a minus 5. Oh, is there another question? Why is it m minus 1? Because I took all of these m's and dropped them by 1. And thank you. This started at 1, and I dropped it by 1 to get 0. And so all these jump up by 1, which make that an m plus 1. Good catch. Another reason you should ask questions. Maybe they really need asking. Okay. All right, last step is I want to have a plus 2 in the numerator. And the way I do that, of course, is I take this previous function and I multiply it by the constant. Let's see, minus 2 over 5, right? So when I divide it by minus 5, it'll put a 1 up here. And then when I multiply it by a 2, it'll put the 2 up there. So I've got to do that to the general term here. So I'm going to multiply it by minus 1. And I usually do those separately because it's really just easier to keep track of that way. So I'm going to change the sign of this, and I'm going to do it by simplifying this from m plus 1 to m. You could add another one to it. It would actually be true to say that it's m plus 2, but it's nicer this way. So if I multiply by minus 1, it's going to change the parity. Where it was positive before, it will be negative and vice versa. So if I just adjust it by 1, that'll do it. When I divide it by 5, this factor of 5 to the m plus 1 becomes 5 to the m. And then I need an m plus 1. It doesn't affect it at all. And let me see, what have I missed anybody? Yes, I have. I have divided by 5, that's accounted for here. I've changed the sign, that's accounted for here. And then I need to multiply it by 2. That's accounted for here. And then I need to get my factors of x. So that's it. So there's a power series expansion for this function. And I should probably say that if you wanted to, you could write out a few terms and do the old calculus ... notation. So when m is 0, I have 2 times 1, 2 times minus 1 to the 0. 5 to the 0 is 1. When m is 0, this turns into a 1. And when m is 0, this turns into a 1. That's kind of a complicated way of writing 2, but that's what you get when m is 0. When m is 1, you'd have 2 times a minus 1, so it's probably more convenient to write this as minus 2 out of here, times 5, 5 to the 1. When m is 1, this is another 2, and that is x to the 1. Then I'll do one more. When this is m is 0, m is 1, m is 2. When m is 2, this turns into a positive, so I get 2 times 5 squared times 3 from this times x cubed. And things go on and on, plus, minus, plus, etc., forever. And there's actually a formula. The formula is sitting right there in front of us. Okay, any question about that? Now, if I had a follow-up, and I said, okay, do it again, well, this time I want a 3 down here, how would the procedure change? So in other words, I want 1 plus 5x to the 3rd power in the denominator rather than the 2nd. How did I get the 2nd power this time? Yes. Yes, take another derivative. Is that your suggestion too, Linda? Yeah. So yeah, if you take one more derivative, then you'll get a -3 power here, right? And you'll get some other constants, but they don't matter because you take out and put in what you need at the last step. So were I to take a second derivative here, I'd get +2, 1 + 5x to the -3, and then I'd have 2 chain rule factors of 5 out here. And then I'd just clean up that, I'd have a couple of 5s to get rid of. I wouldn't have a negative. And I could get, any small power that I want in this way. Now, if somebody says, okay, get it for me 2 over 1 + 5x, oh, the 1 had disappeared. 1 + 5x to the 20th. Well, this is not going to be a fun way to do it, right? So hopefully, if you did a few of these derivatives, if you really needed that, you'd be able to see the pattern, figure it out. And you probably could. But sometimes it isn't that nice. But we don't always use derivatives either. Now, if I had asked for something like, I didn't, but what if I had asked for the log of 1 + 5x? Well, it would be very similar. These first few steps, I would get around to 1 over 1 + 5x. That's this. And then if I take an antiderivative, it would give me something involving the log of 1 + 5x. So an antiderivative here would also be possible. This would then go to x to the m + 1 over m + 1. So you could get something in the denominator. So this sort of thing is definitely possible by taking antiderivatives. So derivatives and antiderivatives, the bottom line is don't forget about those. Those are perfectly good tools to use for generating series. And they oftentimes work quite nicely. And this is a case in which they do. All right, so that's one way of getting series. You start from a known series and you sort of think of manipulations one step at a time that walk you around till finally you get to the goal. And what can you do? Not a lot. Substitutions, derivatives, and antiderivatives. And then you can multiply by constants. And I don't know what else to say about that. That's pretty much the end of the list. There is another thing you could do though. So let's take this function, which this one, this or a related example, I always enjoy doing every semester. And if you see the secret right at first, you can be polite and keep it a secret. Okay, find the power series expansion for this function. F of x equals 3x squared minus 2x plus 1. Now, if we could think of a known series, maybe we could manipulate it around to get it that way, but there is another way of doing this, and that is through the Taylor series formula, which in general says this. Maybe I should not give it in general. Take the mth derivative. That's the parentheses around here mean derivative, not power. Take the mth derivative at 0 of the function, divide it by m factorial, and then multiply it by x to the m. This is for a series that's centered at 0. You can center it at another place. In calculus books, it's almost always, the center is almost always called A. So if you're used to that formula, you would write it this way. It's not a great way to write it for this course because we tend to write coefficients as A sub m. And so in an analysis or advanced calculus or differential equations course, you typically would see it written this way, x sub 0. It's that special x at which we center the series. And that's at 0. Okay, what that means is you take derivatives, you divide by a factorial, and you multiply by the corresponding power of x, and you've got your term in the series. So what we're going to need to do in order to apply this method is we need the original function evaluated at 0. And then its first derivative evaluated at 0, and its second derivative evaluated at 0, etc. So second derivative could write this way, or you could write it with the primes. Not so convenient when you get like to the fifth derivative. So that's why people use this. Okay, let's get some of these. The original function evaluated at 0. Well, I get 0 minus 0 equals 1. And then I need the first derivative. Well, the first derivative is 3x minus 2. And then when I evaluate that at 0, I get negative 2. And the second derivative is the function that's always equal to 3. And so when I evaluate that at 0, sure enough, I get, it should be 6 though, right? Right here. 6x minus 2, first derivative, 2 times 3 is 6 for the coefficient. And that means when I evaluate it at 0, I still get a minus 2. But this one is 6. Okay, so I'm ready to write down my series. Well, I should explain why I'm ready. Well, if I take the third derivative, I get 0, right? And if I take the nth derivative, I get 0 if n is greater than or equal to 3. So all the rest of the terms in the series, there are officially infinitely many of them, but infinitely many of them are equal to 0. So you don't have to bother writing them. After m is 0, m is 1, m is 2, that's all there is to this series. So f of x is equal to, we're going to write down what the formula means. It says, take the 0th derivative, so that's the original function evaluated at 0, divided by 0 factorial, multiplied by x to the 0. That is this formula when m is 0, right here. First derivative. You take the first derivative, evaluate it at 0, divide by 1 factorial, and multiply by x to the 1. Then you take the second derivative, evaluate it at 0, divide by the 2 factorial, and multiply by x squared, and everything else is guaranteed to come out to be 0 because the higher order derivatives are all zeros. Okay, let's plug them in. F at 0 is 1. 0 factorial is 1. And x to the 0 is 1. First derivative, evaluated at 0 is negative 2 over 1 factorial, which is 1, x to the 1. And second derivative at 0 equals 6 over 2 factorial, x squared, and then a bunch of zeros. And so I get 1 minus 2x plus 6 divided by 2 is 3x squared. Does anybody notice anything about this? I started here, find the power series expansion for this function, and I ended here. Well, I got what I started with, right? Which is encouraging. At least the formula isn't wrong. If you start with 1 minus 2x plus 3x squared, and you apply Taylor's theorem, this formula, you get what you started with. Which is to say, we started with a power series, And we ended up with the same power series we started with. This, our original function is this, right? And it's perfectly legal to write it in this order. And it's also perfectly legal to add any number of zeros we want to the end, right? So this, whoops, I lost my 2 there. This is already the power series expansion for F. And so when I applied the formula, I got the original thing back. And that's actually what it should do. It should do that. So why did I show you? Well, for a couple of reasons. Number one, to convince you that the formula is doing something sensible. It does actually work. Number two, if you think about it, this would allow me, I could change this center, right? It would allow me to say this is equal to some constant plus some other constant times x minus 1 plus some third constant times x minus 1 squared. In other words, I could shift the center of this series. And if you applied Taylor's formula, you would in fact find out what these numbers are. Now, it's not the most efficient way to get there though. If you really wanted to just shift this, it's way easier to do something like this. Well, what is f of 0? Well, you look at your original function, which is way back here. F at 0 is equal to 1. So then you would plug in f at 0 here, and that gives me C1 minus C2 plus C3. And that has to be equal to 1. So I got an equation in C1, C2, and C3. Then I could look at the first derivative at 0. Well, the first derivative at 0, I've already done that calculation somewhere. It's minus 2. And if I took the first derivative of this series, here it is. If I took the first derivative, this would drop out, right? Derivative of constant is 0. This has got a 1 on it, so this would just be C2. And then I'd have 2C3. And when I plug in a 0, I'd get 0 minus 1 squared plus 1. And I think, yeah. And that's equal to negative 2. And in the same way, I take the second derivative, evaluate it at 0. We already know what you would get. We have done it before. You get 6. And if I take two derivatives on this, I get 2 times 1 times C3. So I get a system of equations. That's a much more efficient way to shift this center. And it has the nice feature that that's the first thing we did in this course, right? Systems of equations. So that would be a more efficient way. But you could set a or x0 equal to 1 and apply this formula, and it would give you the shifted form of this polynomial. Why would anybody want to do that? If you're trying to evaluate this polynomial with very, very high accuracy near x equals 1, you would probably want to do it that way. Because these things, as you get x's that are very, very close to 1 and start raising it to powers, you get numbers that are close to 0, and this becomes the most significant term. It reduces round-off error to do shifting. So suppose we wanted to evaluate this original function, around x is 30. You don't want to use this form. You want to adjust it so you have a constant plus x minus 30 minus x minus 30 squared. You want to redo it that way. And then you get far, far less round-off error. So in numerical analysis, shifting series is something you do all the time. Okay, let's see. Let's do another one. Let's find a series for hyperbolic cosine of x. Well, we have a related series. E to the x is the sum. M goes from 0 to infinity, x to the m over m factorial. By the way, take a look at Taylor's formula. E to the x, all of its derivatives are equal to itself, right? And all of its derivatives evaluated at 0 are equal to 1. E to the 0 is 1. So in Taylor's formula, this thing right here turns into a 1. 1 over m factorial x to the m. That's where one way of getting this series. Another way is you could look on the notes that I handed out last week and say, well, Dr. Sprague said that e to the x has this series. And he might not be that smart, but he's fairly nice, so we don't think he would lie. And he probably looked it up somewhere. You know, sure enough, I did when I was in Calculus 2 as an undergraduate. My professor told me, and I believed it. So I've believed it ever since. So there's e to the x. Now, how would that be helpful for hyperbolic cosine? Well, it would be helpful because that is hyperbolic cosine is e to the x plus e to the minus x over 2. Or you could express it this way, it's 1/2 of e to the x plus e to the minus x. All right, so let's go after it that way. What I'm going to do is write my series for e to the x. And then I have to subtract the series for e to the minus x. Now that is actually not very hard to do, to get that series. It is something to generate, but all I have to do is take the series for e to the x and replace x by minus x. So I have minus x to the mth power. In other words, minus 1 to the m, x to the m over m factorial. And I add those two series up and divide the result by 2. Now, by the time you get really comfortable with these formulas, your next step is you just write down the answer. It's not too difficult to see what this does, but the first few times it's worth writing out some details. So let's write out, say, I don't know, 3 or 4 terms of this, and we'll do the same for that, and we'll see what happens. So I'm going to put some parentheses here, not because I need them, but I want to be clear which terms come from what series. So for x to the m over m factorial, when m is 0, I get x to the 0, that's 1, over 0 factorial, that's 1. Then when x is 1, I get x to the 1 over 1 factorial, and 1 factorial is 1. Then for m is 2, I get x squared over 2 factorial. Well, this is easy enough. Let's go ahead and write down another term or two. It's x to the 0, x to the 1, x squared, x cubed over 3 factorial, x to the 4 over 4 factorial. Okay, plus dot, dot, dot. Subtract off what we get from this next series. Now the next series is exactly like the first series with one change. It's alternating in sign. When m is 0, you get a plus. When m is 1, you get a minus. When m is 2, you get a plus. When m is 3, you get a minus, etc. So all we got to do is copy this, but just make it alternate, starting with a plus. Plus minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4 over 4 factorial. And this goes on like that, minus, plus, etc. And then let's see what's going to happen. Well, we have 1 minus 1, that adds up to 0. Then we have x minus a minus x, that's 2x. Then I have x squared over 2 minus x squared over 2, that's 0. So the x squareds go away. X cubes, I have x cubed over 6. Well, let's call it 3 factorial. X cubed over 3 factorial minus a minus x cubed over 3 factorial. That will be 2 times x cubed over 3 factorial. Then the 4th power terms, well, both of these are pluses inside the parentheses. So when that distributes, those will add out. And you can pretty much guess what's going to happen. The next one won't add out. The fourth power terms add out. 5th power terms survive. We'll get 2 of them. X to the 5th over 5 factorial. And it goes on forever. And what happens now is this half distributes here and kills all the 2's. So you get x to the 1 plus x cubed over 3 factorial plus x to the 5th over 5 factorial. And you probably can see the pattern by now. It'll be x to the 7th. Oh, yeah, over 7 factorial. I'm only getting odd terms here, which is odd since this is an even function. What did I do? Oh, I put a minus right here. Well, this is so easy to fix. You're going to love it. Change this to a minus and change this to cinch. Oh, and put a minus here. I did all this calculation as if I had cinch. It's right, there's actually an error. I had a plus here, and then when I copied it, changed it to a minus. Why? I have no idea. None whatever. It was wrong. But rather than, by this time, I have to change everything. So change the problem. Okay, and I should be clear, this doesn't stop there, it goes on forever. So I have now created a series for cinch. By the way, sine x equals this. It was one of those series you should know that I put on the first handout. It's minus 1 to the m, x to the 2m plus 1 over 2m plus 1 factorial, which is nothing other than this series, with the exception that it alternates in sign. So yet another reason that people think that this is a function worth talking about. It has a power series expansion very, very similar to the one for sine of x. And it has a really nice, expression in terms of e to the x. And sinh and cosh have nice relationships when you start taking derivatives. So, why did people invent this? Because it's handy. That's why it pops up a lot in physical science kind of applications. Okay, so now I need to change my original question. Find a series for cinch. And my mistake will have nice benefits for you later on if you keep these notes. But I won't say any more about it right now. Okay, any question about this? All right, now, how would you use this to solve differential equations? Well, let's take this deep and profound equation. I wonder if any of you know the solution to this. Well, yes, I think e to the x and any constant multiple would work. Yes, that is correct. And that's not such a bad thing. C e to the x is the solution here. Since we know what the solution is, hopefully we could see that come out in this technique. So this technique works in the following way. You assume that the solution has a power series form. Now, there are theorems which tell you when that is true, but this is a linear equation. And if you have a linear equation with what are called analytic coefficients, then you will have this kind of a solution of it. You have at least one solution of this form. And analytic simply means that it has all orders of derivatives. So it's got a first, a second, a third, a fourth, a 257th derivative. Any order you want to mention, it has that derivative. And if you think about the Taylor series expression, that has a derivative in every term, right? So as long as you've got those derivatives, you can come up with the Taylor series expression or the power series. Okay, now I'm going to need one derivative here, and we're maybe not professionals yet, but we're at least not beginners. So we know this is going to start at 1 am times m x to the m minus 1. And we also know that at some point in time, we receive some good advice that says, you know, your life will be easier if you, when you're working with the power series method, if you always adjust it so things are indexing on x to the m power. So now I'm going to clean this up. Let's see. Now, what I want to do is push, I want to push these up by 1, right? Which means I knock that one down by 1. So this will be 0. Then these go up. And rather than write the m here, I'm going to put it in front. So m plus 1 now. am plus 1 x to the m. So that's a power series expansion for y prime. That's the power series expansion for y. And now I'm going to plug those into this equation, y prime equals y. Okay, so y prime, maybe I should repeat that. Y prime equals y is what I'm working on here. So I've got the series, m goes from 0 to infinity, m plus 1, am plus 1, x to the m is equal to the power series expansion for y. M goes from 0 to infinity, am x to the m. Now we have a really, really useful theorem. It says this: if you have a power series which adds up to the 0 function, it's not just 0 for some particular value of x, but it always adds up to 0 for any x. There's only one way to get that. Am has got to be equal to 0, and the symbol in math is this one. It means for every. And in fact, people usually write it this way as a condition. For every m, am equals 0. So I'm going to write it in the standard way. Should take it off of there. All right. So what I'm going to do is manipulate this around so I only have a single series. So what I'm going to do, of course, is just like what we would do in algebra. Well, I guess it is algebra, but like in high school algebra, is you gather everything together, right? So I'm going to put these two series on the same side of the equation. So what I'm doing is I'm going to get a single series equal to 0 and then say every single coefficient must be 0. And that is not hard because I've already adjusted this so that the powers on x are in agreement and they both start at 0. So all I've got to do is this. I've got m plus 1, am plus 1 minus am, and that is the coefficient on x to the m, and that sums up to 0. In the sense, mathematicians oftentimes write 3 bars when they're trying to emphasize this point, in the sense that no matter what x is, you get 0, not just for some single x. And that tells us then for every m, m plus 1, am plus 1 minus am must be 0. And you can solve this for am plus 1. You get am over m plus 1. And this is known as a recurrence relation. If I know what A0 is, it tells me how to compute A1. If I know what A1 is, it tells me how to compute A2, et cetera. So turns out I do know what A0 is. It's A0. And that's not as silly as it sounds. So we'll just say it's got a constant term, A0. All right, now what's A1? A1 is A0. What I'm doing is taking this formula right here and I'm setting m equal to 0 in this recurrence relation. It's A0 over 1, which is A0. A2 is, well, I set m equal to 1 in my formula. A2 is equal to A1 over 2. But A1 is A0. So that is A0 over 2. I'll leave it for that for now. M equals 3, or rather M equals 2 is the third coefficient. I'll get A2 over 3. Good general advice on these is don't be too quick to simplify. So A3 is A2 over 3. Well, I know I have an expression for A2. It's A0 over 2, and I want to divide that by 3. So it's A0 over 3 times 2. A4, after a while, you start seeing the pattern. Notice this denominator matches that subscript. So I take the previous expression and divide it by that subscript. That's all you got to do. So A4, I'm going to take this expression, A0, and divide it by 4. So I have 4 times 3 times 2 down here. Now, of course, you can multiply those denominators by 1, right? And so this A4 is A0 over 4 factorial. A3 is A0 over 3 factorial, et cetera. So this is A0 over 1 factorial, A0 over 2 factorial, A0 over 3 factorial, A0 over 4 factorial, et cetera. And now you could plug this back in to your formula for y. Y, we said, I don't know where, it's on the page somewhere, but I will quote it from memory. Y is this. And now I have a formula for y. Everything, absolutely everything has an A0 on it, so you might as well write that on the outside. A0 times the sum, m goes from 0 to infinity, and now we'll just ask ourselves the question, what is am? Well, it looks like am, A4 is A0 over 4 factorial, am is A0 over m factorial, and I put the A0 on the outside, so I'm getting 1 over m factorial x to the m. And then you say, oh, I recognize that series. It's e to the x. So we solved it with a power series. Questions, objections, deep heartfelt sighs? All Okay. It's a constant. Yeah. Remember, the solution, as we normally write it, is this. And what we've said is, well, A0, I don't know what it is, make it up to be some value. Once you've decided that, it fixes the rest of the solution. All right, I am really short on time, so I'm not going to be able to give you details on this one, but I should show you this because there's a homework problem related to it. And the problem is I don't remember exactly which homework problem I gave you. So I'm hoping that I am not stepping over the homework. Suppose we wanted to solve this by power series methods. What you would do is you would start in exactly the same way that I did before. And then you would take two derivatives. When I take two derivatives, now notice I'm leaving the starting point blank right now. I'll come back to that in a minute. So at the moment, I'm just going to look at x to the m and take two derivatives on it. m minus 1, x to the m minus 2. And my habit is to write these m's to the left of the am. And now the idea is this starts with a 0, then it's a1x plus a2x squared, etc. It's just like polynomials. Every time I take a derivative, I'm going to lose a term. The constant term drops off. So if I took one derivative, this starts at 1. If I take two derivatives, it'll start at 2. And if you write this out term by term, you would see that, if it isn't obvious now. And then, oops, I didn't put my primes on there, y double prime. So now I would like to readjust this so I have x to the m here. That means I push these m's up by 2 and drop the outer one down by 2. And I'm going to be really careful so Sam doesn't say, hey, you got that wrong. Okay, so I'm dropping the outside down by 2. I'm lifting the inner ones up by 2. So this is m plus 2, m plus 1, x to the m. You always want this for this method. You want these x terms to be x to the m. Now, when I write my equation, of course, I'm going to push everything to the left-hand side. I'm going to write it this way, and I'm going to get this series for y double prime minus the am x to the m series for y. And then when I subtract them, I say, oh, look, this is just like a polynomial. I've already got my powers of x's lining up. They're both starting at 0. So you just subtract the coefficients. Oh, this guy lost its am. Oh, my goodness, it got lost way back here. So when I took these m's and bumped them up by 2, this one had to go up as well. So that is missing an am plus 2 there. So I get this big grand series here, square bracket, m plus 2, m plus 1, am plus 2, minus am, square bracket, x to the m, and it all adds up to be identically 0. You apply the theorem. Oh, this added up to the 0 function. every single one of these must be, for every m, this expression must be equal to 0. So I set this equal to 0 and solve it for am plus 2. And I'm skipping some steps because I'm short on time and I really wanted to get to here to show you what to do. What you do is, this is going to split into 2 columns, okay? I'm going to select a value for A0. Having done that, hold on here. Okay, well, I did it again. See this? I'm solving this equation, but I announced at the beginning I was solving this equation. Well, it's too late. Just take out the 36. I am solving this equation. If you didn't catch that, just take out that 36. Why? Because I accidentally threw it away later. It'll be fine. It's a perfectly good example this way. Okay, now notice now that these are related by a jump of 2, not 1. If you know A0, it will tell you A2. And setting m to be 0, you get 2 times 1 down here. Suspiciously like a factorial already. The next one we're going to get is you go from 2 to 2 more, or A4. And that will be 4 times 3. I'm getting that from here. When I set this to be a 4, that's m is 2, I'll have 4 times 3 times, in the denominator, times the previous coefficient, which is A2. And A2 is A0 over 2 times 1. And you say, oh, what a surprise. 4 times 3 times 2 times 1, that looks like a factorial. After you do these, a few of these, it's not a surprise. The other little detail here is, okay, that's too bad. It's mucking up the coefficients at the beginning. It's changed the solution I had in mind by quite a bit. Okay. Then I am going to have that pattern one more time, 6 times 5 times the previous. A0 over 6 factorial. And at this point, you can probably guess the pattern. A sub 2m, it looks like we've got A0 over 2m factorial. What that is telling us is that we get a solution that only involves the even subscripted terms. So Y1, a basis solution, is going to be this. It's going to be A0. That multiplies everything, right? So that A0 is a free choice. But then you're left over with 1 over 2m factorial x to the 2m. My pen quit. Notice this subscript, always and forever, is matching the power on x. That's how we set it up way back here. This subscript matches the power of x. So that's how I know that I've got x to the 2m up here. Well, that happens to be, well, let's see. If this were alternating in sign, then you'd be getting that alternating series, factorials in the denominator, and even powers of x in the numerator. That would be the cosine. But when it's not alternating in sign, that would be the cosh. And you can probably guess what the other solution is. Y2 turns out to be A1 sinh of x. And you get that by doing this. You start into the recurrence relation this way. A3, you go back here and set m equal to 1. A3 is A1 over 3 times 2. And then A5 is A3 over 5 times 4, but A3 is A1 over 3 times 2. So, and then in that case, you get an A1 cascading through the whole thing, and that gives you a sinh. So with a second order equation, you should expect this to happen. Once you get your recurrence relation, then your process of computing solutions is going to split into some version of even and odd. If it were a third order equation, you would get things divisible by 3. Things when divided by 3 have a remainder of 1, and integers when divided by 3 have a remainder of 2. It would split 3 ways. So you get three different functions. And by the way, that gives us some insight now. With linear equations, we said, for homogeneous ones, you should expect for first order, you get one basis function multiplied by a constant, right? For second order, you get 2 basis functions multiplied by constants, add them up. For third order, you get 3 of them multiplied by constants, add them up. Why does that happen? Well, this is one way of answering the question. You see that this splits into 1, 2, or 3 sequences from the recurrence relation. If this is m plus 1, you get 1. If it's m plus 2, you get a split of 2, m plus 3, a split of 3, etc. Okay, so this is an example of solving a second order equation. What I'm going to do is I'm also going to post notes, completed notes like this from, I think it's probably the last time I taught the course. So it's got a couple more examples. So you can follow them if you need them for tracking with the homework. And there is a homework assignment posted, which I would like to have from you on Thursday. And with that, we will end.